end, you can directly ask questions for discussions with Sir. So hello and welcome you all to the 8th lecture of the Nature as We Unfold It seminar series of CAPSS. I am glad to introduce our today's speaker, Professor Subhasis Chattopadhyay. Professor Chattopadhyay currently heads the High Energy Physics and Applications Group at Variable Energy Cyclotron Centre. He is also holding an adjunct professor position at Bose Institute, Kolkata. He completed his bachelor's in science from Bakura Christian College and his MSc in physics from the University of Calcutta. He did his MTech in materials and science and engineering from IIT Kharagpur. After that, he joined BARC Training School and he completed his PhD from VECC under the University of Calcutta. Professor Chattopadhyay has worked on instrumentation, phenomenology and physics analysis in the field of high-energy heavy ion collisions at CERN and Brookhaven National Laboratory at USA. He is currently coordinating India's participation in the FAIR project at Germany. He is presently holding the He has made significant contribution in detection and study of photons and dielectrons in heavy ion collisions. Professor Chattopadhyay has supervised more than 15 students so far. Currently, he has 8 PhD students whose PhD is ongoing. I would also like to take the opportunity to mention that 2 of his PhD students, namely Dr. Shaikot Biswas and Dr. Siddharth Prasad, are currently faculties at the Department of Physics of Bose Institute. He is a recipient of Homi Bhabha Science and Technology Award from the Department of Atomic Energy. He is also a Fellow of National Academy of Science, India. And now I would like to quickly start our today's episode. And I would forward the mic to Sir so that he can start.
Thank you, Shreya. Now, first question is, do you see my slide?
Yes, sir. Yes, sir. We can see your slide.
So I just changed the slide and you will confirm that yes, it's changed. Has it changed?
Yes, your slide is changed to page 2.
Okay, so let me start. I am extremely sorry for this trouble. It happens. It happened earlier as well. But I must thank all of you for patiently waiting for this presentation. Now, my presentation today is in some sense not a very kind of deep scientific presentation, but it's kind of sharing my thoughts to all of you, just because some of you are working in some field, some others are working on some different field. So I just wanted to share my thoughts on a very interesting topic nowadays being discussed worldwide, which is big science and small science. Now, to give you an example, that you might have a colleague or you might have your friend who are working on an experiment which is being done on a tabletop, and the results can be obtained the next day, the paper can be written the third day, and that's how it might go. And maybe someone else is working for 20 years to build the experiment, and then the data taking is done, and that may end up in some other years. So let me start with something which is my slide number 2. This is basically a list of Nobel Prizes starting from 1901. I'm sure you have seen at the beginning of this, which is called 1901, and then it's called physics. It's mostly physical sciences, so physics and chemistry. And I'm sure all of you know, not that anybody is not aware of it, but just to give you a repetition, that's Röntgen, who got his Nobel Prize for the discovery of X-rays. The discovery happened in 1896, and of course there was a photographic plate with which he discovered his X-rays or unknown rays. Of course, now you look at the timeline, which is on the left. So next, go to 1903, which is Becquerel and Madame Curie and Pierre Curie, which is for radioactivity using a photographic plate. Then 1905, which is again in physics, which is Philip Leonard, which is for Leonard window. That's the discovery. This is a phosphorylation material which we nowadays use. 1908 in chemistry is Ernest Rutherford for the discovery of atomic nucleus. 1927 Wilson for cloud chamber, discovery of cloud chamber. 1935 Chadwick, which is for discovery of neutron using ionization chamber. 1936 Hayes and Anderson, discovery of cosmic rays and positron. Now, after 1936, let's go to another one, which is 1948, maybe a 12 hours gap, which is Blackett, which is for E plus E minus production using advanced cloud chambers. Then 1950, this is Powell. I am sure all of you who are a Bose Institute student has some memory, or you have been told that the discovery of pion, for which Powell got Nobel Prize, can very well be credited to Professor D.M. Bose of Bose Institute. And this was in 1947, the discovery. Then Walter Bothe, who is for coincidence method. Then 1958, Pavel Cherenkov for Cherenkov radiation. Then Sergey and Campbell in 1959, which is for antiproton discovery. Then Glaser for bubble chamber. Then comes a little bit bigger. These are all kind of discoveries starting from X-rays till bubble chamber, is to an extent, in my opinion, are smaller scale today, because these are like tabletop experiment. Then comes 1976, which is the discovery of the Jepsi meson, which is a bound state of charm and anti-charm quark, which was discovered in two different places. One is in Brookhaven National Lab, which is AGS synchrotron, using proton beryllium collision, and another one is E plus E minus collision in Stanford. And these JEP and Psi are two different names. Samting is for J. And then, of course, 1980, this is a Cronin effect, which is for CP violation. And then now 1984, we are already in this era, basically. 1984, many of us are born and maybe might have started our career, which is Carlo Rubbia and Simon van der Meer, which is at CERN for discovery of W and Z boson. Then 1988, Lederman, Schwartz and Steinberger for muon neutrino. 1990, Friedman, Kendall and Taylor for proton structure, then spin of proton. Then again, Demelt and Paul for electron G2. Then Charpak, which many of you might know, in 1992 in multi-or proportional chamber. And Raymond Davies for cosmic neutrino. And very recently in 2013 for Higgs discovery by CMS and Atlas experiment. And gravitational wave in 2017, which is just 3 years earlier, which is for LIGO. So now, by showing this list, the point which I am trying to, do you hear me? Please, can you please confirm?
Yes, sir.
Okay, thank you. Okay, so by bringing this list to you, I just wanted to give you an impression that how physics has changed over the years. So while in 1901, if somebody tells you today that for discovery of X-ray somebody has got Nobel Prize, you might understand. I mean, somebody who knows X-ray so much, maybe today's kid, they will say, what is there to discover? So there are two things which I have brought in this list. One is, of course, the discovery happened very fast. 1901, 1905. That was the time in 20th century that things were evolving. We were understanding the mysteries of universe one after the other quickly. And of course, they were all awarded for Nobel Prize. But then things have changed. The scale have changed. When we first understood our Maxwell equation, then you have to make it complicated. And then you try to understand more and more mysteries of nature. And interestingly, as you try to understand deeper and deeper, your equipment becomes bigger and bigger. And then you come something with gravitational wave or even Higgs discovery, which are the huge equipments of 10,000 tons or 12,000 tons compared to the X-rays that you are talking about. So the point what I'm trying to make here, just to all of you, that's the one where we have made a clear transition. Maybe it's a continuous transition, not a first order, second order, where we have gone from big to small science. So let me define it. Let me define it as per Wikipedia. What is big science? Big science is a term used by scientists and historians of science to describe a series of changes in science which occurred in industrial nations during and after World War II, as scientific progress increasingly came to rely on large-scale projects, usually funded by national governments or group of governments. So this is suddenly means whether you talk about CMS, ALICE or whatever, you can see the number of people, amount of money that is spent. That suddenly is not with the individual or small group efforts or small science. That is are still relevant today, as theoretical results by individual authors may have a significant impact, but very often the empirical verification requires experiments using constructions such as the Large Hadron Collider, costing between 5 billion to 10 billion dollars. So what are the features of big science? Big budgets, no longer based on philanthropic. It's like our Mahendralal Sarkar and cultivation of science, or even your Bose Institute. It has to be funded separately. Big staff, so it cannot be just one or two people, they do it. So it is across the globe. And of course, there is the issue of authorship, who will go, because Nobel Prize cannot be given more than 3 people, individually at least, unless it's a group. Big machines, Lawrence cyclotron as the first example, and big laboratories, like centralization of facilities like CERN. And what is the small science in the same context? It refers, in contrast to big science, to science performed in a smaller scale, such as by individuals, small teams, or within community projects. So, let me take another statement which was said by Arvin Weinberg, who was the director of Oak Ridge National Lab in science in 1961. He says, when history looks at the 20th century, she will see science and technology as its theme. She will find in the monuments of big science, like the huge rockets, the high energy accelerators, the high flux research reactors. These are the symbols of our time, just as surely as she finds the Notre Dame a symbol of the Middle Ages. We build our monuments in the name of scientific truth. They build theirs in the name of religious truth. We use our big science to add to our country's prestige. They use their churches for their city's prestige. We build to placate what ex-President Eisenhower suggested could become a dominant scientific caste. They built to please the priest of Isis or Osiris. Now this is my kind of motivational slide, almost the last one, that there is a combination of 4 papers. The first one, there is only one author, who is E. Rutherford. And the title of the paper is The Scattering of Alpha and Beta Particles by the Matter and the Structure of the Atom. There is one author, Rutherford, which in my opinion is the beginning of nuclear physics. Then on the right, where I have seen VECC experiment, I am one of the author. When I first joined VECC, I joined this experiment, it was published. You can count it, maybe 10 or 15 maximum. Then you go to just below that, which is WA98, event by event fluctuations of particles. There also I am an author, and maybe it's like 45 people. And then go to the left, which is STAR, solenoidal tracker at RIC at Brookhaven National Laboratory. This is gold-gold collisions at 62 AGeV, and there are something like 250 authors. And now if you look at the author list of ALICE or CMS or like that, then there are 100 institutes and maybe 1,000 authors. So that itself sets the scale, changes in scale from one author, which of course is worth getting Nobel Prize, to 1,000 authors, which of course is also worth getting Nobel Prize, because this essentially discovers new things, but then the requirement is different. Why does it happen like this? Why do you need bigger and bigger machine to go deeper and deeper? You all know about it, I am sure, that if you want to look at the matter, if you look into the atom, then you need an extra magnification, which is of the order of 50 micron, and like cells, and you need microscope. If you want to look at the DNA, which is like 2 nanometer, you need electron microscope. If you want to look into the nucleus, that means protons and neutrons, then you need an accelerator like VECC, which is like a 220 centimeter diameter machine. And if you want to look even deeper, that means like quarks, which is like 10 to the power minus 18, then you need something like LHC, Large Hadron Collider, which is 27 kilometer ring. There was a recently, I think there was many of you have participated in this, that there was an exhibition, moving exhibition, which concluded last year, just before the pandemic, which essentially showcased the mega science activities in which India participating. And this is what is the photograph of the first one, where Dr. Saraswat inaugurated along with Professor Vijayaraghavan, who is the principal scientific advisor to the Prime Minister in Bombay. Now, before going into some of the details of those big science activities, I want to give a list. These are the ones which are shown in that exhibition. One is ITER, International Thermo Nuclear Reactor. This is in crore, 1,75,400 crore, and this is what is the Indian contribution, 15,375. And that's happening in France. Then you go to CERN, which is LHC basically, 80,000 crore. And India has, apart from the experimental part, there is 80 crore per year associate membership. It's in Geneva. Then, of course, FAIR, Facility for Antiproton Ion Research in Germany, Darmstadt, Germany. It is 16,000 crore and 700 crore from India. Then Square Kilometer Array, the first one was a different type. The next two are the accelerator based, and the rest one is astronomical based. So Square Kilometer Array, this is the number 6,400, and India's contribution is 500, which is in Australia. 30-meter telescope TMT, which is 11,300, which is 1,300 from India, and the location is not decided yet. IONO is our own project, about 1,583, which is in Tamil Nadu, Theni. And then LIGO, this is Gravitational Observatory, which is 12,000 crore, and India is 3,000 crore, and it's in Maharashtra. Of course, in my list, I just showed the ones which are showcased there, but certainly I have missed. I did not cover anything with space science, which are even more expensive, or the bioscience, which is also equally expensive. I just have one slide made for bioscience, because Bose Institute, being a bioscience institute, has certainly have a lot of interest to that, which is the Human Genome Project. Many of you might be knowing about it. And then the cost of the Human Genome Project is 2.7 billion, which is in 1991 project, which is kind of similar as ITER or LHC. Now let's go one after the other, maybe rather quickly, to some of the projects that I have mentioned here. One is the ITER. ITER is in France. This is a fusion reactor prototype project. It will not create you energy, but it will at least show that yes, fusion reaction, the energy can be contained. The way to a new, clean, safe, and nearly unlimited energy. And it is a multinational, as you see, a lot of flags. And it's a multinational scientific collaboration. This is again the hallmark of any large collaboration, that one institute, one lab cannot do it. It has to be multinational. Without equivalent in history, a large-scale experiment to demonstrate the feasibility of fusion energy. Fusion energy is the energy which runs the stars and sun. How does it work? So you know fusion, it's a deuterium and tritium, hydrogen isotopes, they fuse, and then they create energy that you must have read, I am sure, in many levels. And then the energy is carried by neutron, which hits the wall, and then it is sustained by helium, which essentially inside this. But the point is that in case of fusion, if you want to have it, then you have to have 150 million degrees centigrade temperature. So anything which is contained inside this temperature, that will essentially melt. So we have to have something that this plasma, which is of 150 million degrees centigrade, doesn't touch the wall inside which the fusion happens. And still then, the neutrons which are coming out of it has to generate the heat, and that heat has to be like a thermal power station. That heat has to be transmitted as a steam or something else to generate energy, electrical energy. So how do you contain this fusion plasma, where the fusion is happening, the energy is there, and 150 million degrees. So the hot plasma, there has been a lot of, I think Saha Institute of Nuclear Physics also had a program of tokamak. Institute of Plasma Research has a program of plasma research and tokamak. So what is the challenge in this research is to confine this plasma. There are two ways of confining. Of course, one is called inertial confinement, another one is called magnetic confinement. Being a magnetic one, there are particles, electric particles like electron and charge particles. They might be confined and led to move in a circular orbit only inside this by using a magnetic field. So this is what is called tokamak. This is the Russian word, also toroidal magnetic field. So there are helium nuclei which sustain the burning plasma. Neutrons transfer their energy to the blanket. In a fusion power plant, conventional steam generator, turbine, and alternator will transform the heat into electricity. Now there is a history. There is a history in this program. This started in 1985, where I think you are maybe some of you are not born. There were American President Ronald Reagan and that time USSR President Gorbachev. They had a pact, and they said at the Geneva summit that they said there is a collaboration for the benefit of all mankind, and that was the beginning of the ITER. And that time there was nothing, and in August 2010 the construction started, and 2007 preparation work were already done. And today, as I have shown some of the pictures, and I will show more, that the construction site is busy. So as I have already shown, what are the problems there? The main problem is to contain inside a magnetic confinement. And another thing about ITER, because there were earlier fusion devices made, but there the output energy was less than the input energy. It was like 16% of the energy which is go back. Of course, it will not solve your energy problem if you spend more energy than you get as output. So only way you can get your solve your energy problem is to get more output energy than input energy. And that is what is the aim of ITER. In that sense, ITER is a thermonuclear experiment. And there the plan or the aim is to get 10 times more. So you give 50 megawatt and you get 500 megawatt back. That is what is the aim. And this is the challenge. So again, the point for which is the theme of my talk today is that there are many people, many countries together, including our former atomic energy chairman Anil Kakutkar is here, along with other the French president who was there, Mitterrand. And these are the countries: China, European Union, India, Japan, Korea, Russia, and USA. And these are the equipment as is being built by different countries. India is building some of the brackets and the cryostat for the magnet, and other countries are building the entire part. India is, I think, 19%, if I remember correctly. Now, this is what is the status today. This is where the experiment will happen, where it says machine axis, where there will be tokamak. But then, as it is a superconducting magnet which will be running, so there has to be all sorts of association there. Power supply will be there, switchyard, cryo plant, cryostat workshop, assembly hall, and as you can see, it's a big mela which will essentially put together and run this system for doing this experiment. Now I go to the next kind of mega science project. That was the one which I showed. It's called an experiment. That's why it is included. But then it is something which is supposed to solve the biggest challenge on Earth, which is the energy challenge on Earth. So now you have seen, all of you have seen this photograph or this picture, which in my opinion is basically an artist's view. This is the time goes from 10 to the power minus 43 second after Big Bang to today, which is 15 billion years now. And as you can see, there are this picture is very colorful, but then more important is that there are more questions near zero time than answers. And there are of course symbols like G, gamma, W, and all you know, G is for gluon, W for W boson, electron, quark, and all others. So one important thing is that what is happening at every point. So how do you test this? That this Big Bang happens, what are the particles, when those all the forces, four forces, they got separated out, this in 10 to the power minus 10 second, and then after that it cools down, there is an inflation here, and suddenly it gets expanded and it's still expanding. And all these things, if you want to try to understand the universe, only one way is to recreate the universe. How do you recreate the universe? Because the Big Bang is only one, unless you talk about multiverse. So universe is created only once. So how can you go back? There is a joke that okay, let it, you may create it, but then you don't know what happened to that. So there are experiments being done. So this is called mini bang, which basically recreates the universe either in the phase of 10 to the power minus 10 second or in the phase of 10 to the power minus 5 second, where we will test different theories like Higgs boson, whether where the quarks and gluons were freely moving before they got confined inside proton after microsecond of the universe, and you all know about the Large Hadron Collider, which is 27-kilometer ring. So let's take a small break at this point of time. You all have heard, who might not be doing LHC research or something else, you have heard about CERN from some science fiction novel, which is very famous, Angels and Demons. And there is a movie where Tom Hanks played the protagonist of this. Now, what is happening here? Of course, the science fiction movie was very interesting, that the protagonist, he had a lot of grudge with Vatican and he wanted to destroy Vatican. So he how he can do it, and he wanted to do it very kind of silently. So he wanted to put antimatter on Vatican, and then antimatter will annihilate with matter, and then everything will be destroyed. So it is the most scientific way of doing things. And where does he get the antimatter? So he went to CERN. So he went to CERN because there the antimatter is supposed to be made. So there was a vivid description of going downstairs, going underground, and then killing someone, taking out the eyes to get the iris, because all the CERN doors are iris protected, and then going inside, and then finally Vatican was saved as it is there today. But the point what is there here is that why is all those big things being done? Because of the one equation, which is de-Broglie equation, which says that lambda equal to h by p. H is Planck's constant, p is momentum. So if you want to reduce your lambda, that means if you want to go to very small wavelength, very small structure, you have to increase your momentum. So if you want to increase your momentum, there is no other way today but just to accelerate the particle again and again and again to generate the required energy, which will essentially create your mini bang or Big Bang. And that's why there is a statement in this Angels and Demons which says, the protagonist says that so CERN dug out million tons of earth just to smash tiny particles. Because CERN, as you might know, is 100-meter deep and 27-kilometer circumference ring. And this is how the CERN look like. Many of you have been there, and who are not there, this is Geneva Airport, and this is what is the 27-kilometer ring as it has been shown schematically. And CERN is an evolution of activities or accelerators from many decades. So there are smaller accelerators, and they are all used one after the other to slowly accelerate it, and then you go to 27-kilometer ring. And of course, it helps to answer some of the deepest mysteries in science. So there are very interesting statements about CERN, that it's a highest field accelerator. It's a 8.3 Tesla. And iron, if you make it completely magnetic, then you will get only 2 Tesla because it will saturate. So there has to be in superconducting way of making it. Largest superconducting magnetic system, there are 10,000 superconducting magnet. Largest cryogenic system, so it is super fluid helium, 4 degree Kelvin, ultra high cryogenic vacuum, 10 to the power minus 13 atmospheric pressure, the highest current controlled with high precision, of course, highest power converter, sophisticated and ultra-stable magnet quench protection system. These are the hallmarks of CERN. So CERN, the concept started in 83, and then, as you all know, that the beam started in 2010. So this is the timeline that we are talking about, and of course there were issues in at the beginning that there was some problem and it was fixed later. And these are the three experiments that we all know about. One is Atlas, which is the largest experiment, the biggest, 46 meter long, 25 meter high, and 25 meter wide, and 7,000 ton. There is CMS experiment, which is 12,500 ton, and these are the dimensions. And there is a smaller one, which is 21 meter long. Now there is another one which many of you have been working on. It's called ALICE, a large ion collider experiment. And this is what is the picture which was taken. This is the largest magnet in the world. This picture was taken when ALICE was being built. Now, as you can see, this is the youngest member of the ALICE team at that point of time. And today, after this 1983, and if you go today, so it's like 40 years, maybe he is the person who might be the boss of one of the subsystem, or he might be the one who is doing the most of the analysis and supervising students for analysis of data. So the point what I'm trying to make here is essentially that it's a long-term effort, and it needs not only a lot of money, it needs a lot of people, and it needs synchronization. And this is how it happens when they collide. And then these are the particles. This is the challenges so far as detectors are concerned. You have to separate out each of the particles separately, and then only you will get correct kind of physics. And that is what happened in discovery of Higgs. And discovery of Higgs, there are 4 particles, or called two dileptons. That means E plus E minus, 2 of them, or mu plus mu minus. Or there is another collision which gives 2 photons. These are the decay modes of Higgs, and that essentially led to the discovery of Higgs. And as you all know, there are 2 persons. One is Peter Higgs and another is John Englert. They wrote these 2 theory papers. Both are in Physical Review later, 1964. And then there are a lot of activities of all the accelerators and World Wide Web and grid computing. And then they got Nobel Prize in 2013 for the discovery of Higgs. And there is another one, many of you might not know, that LHC is a Large Hadron Collider, where large means 27 kilometers. Of course, it's large, but then it also collides large hadron. That means it not only collides proton, which is a small hadron, but it also collides lead on lead, which are large hadrons. So lead on lead colliding makes you Large Hadron Collider, and this is where we are all interested to see the microsecond old universe. And this is our detector which we built here, and many of you might have participated, and Dr. Prasad is now your faculty. And this is, of course, that there is a discovery that if there are 2 partons which are quarks or gluons, they scatter each other, then one of them gets quenched. So there must be huge dense medium which is formed, like if a particle goes through inside a room and it cannot come out, and that essentially establishes that there is a very dense medium formed, which is called gluon plasma. And so what is the addition there? That we have added one point in the phase diagram where there is the temperature and where there is the baryon density. So you can get inside the quark and gluon free by using increasing higher density also. But then we have added this point after RIC and LHC, which is inside the quark gluon plasma. This is a big contribution of LHC heavy ion program. And now what will happen from today? LHC is still taking data. That will take data at least up to another 30 years. But then the discussion has already started to make one collider. Collider means there are particles come in opposite direction and collide at different points. And this is called FCC, or Future Collider. And this will be 100 kilometer ring instead of 27 kilometer ring, where the discussion is already ongoing. There is another accelerator-based research that many of you know about, which is called Facility for Antiproton and Ion Research. and this is coming up in Darmstadt, Germany. And unlike CERN, here the energy is not high. Energy may be up to something like 45 eGeV for nickel maximum, and but the intensity is very high. That means number of particles are very high. As you know that when you do experiment, sometimes you want to have a high intensity so that things can be done very fast or in a reasonable time. Unlike you have to take years to get a discovery and then nobody will fund you. So these are the countries, India being Bose Institute is the shareholder of this whole project. It's a 2 billion euro project now. We have 3% contribution in that. And there is already a lab existing called GSI, which in Germany called Heavy Ion Research Facility. This has discovered 7 periodic table elements. One of them is Darmstadium, from the name of the place. Another is Hessium, where the state of Hessen. And all the colored ones are the facility which is being built now. And these are the fair facility. And in this facility, the science reach is very wide, unlike and these are the countries who are participating in building this, the orange ones, and the other ones are participating in doing experiment. And the science reach here is very interesting. This fair has a program where there will be science of quark gluon plasma, that means confinement of quarks and gluons, like creating the core of neutron star. Inside the neutron star, where there will be quarks and gluons freely moving, to atomic nucleus or today's planet. So there will be program of atomic physics, nuclear physics, and of course QCD, or quantum chromodynamic research in FAIR. And many of us are working in this field. The construction is ongoing now, and this is what is the main ring, which is a synchrotron of 100 Tesla meter. And this is the tunnel, 60 meter wide and 19 meter deep. This tunnel is being built, and we have supplied already 164 power converter or power supply for building this FAIR accelerator, and we are still continuing with this. Now I come to the another kind of projects. These are also mega science projects by the definition that we have defined at the beginning, which is astronomy. Now, as you know, that there are many kinds of astronomy. Whatever comes from sky, there may be radio waves, there may be microwave, there may be infrared, there may be ultraviolet, there may be X-rays, there may be gamma rays. Each of them needs different kind of detectors or telescopes, and these ones will give different kind of facets about our universe. So there are some ones which will come out in 2021. There are something which might be already operational, and there might be coming in 2031. But the one which we will discuss today, where India is participating, is the LIGO, which is Laser Interferometry Gravitational Wave Observatory, and Square Kilometer Array, which will come up in 2027, and then 30-meter telescope, which will come in 25-27. So let's discuss a little bit more on that. So let's talk about gravitational wave. I'm sure many of you or all of you might already have heard that gravitational wave has been discovered. What is gravitational wave? When two bodies, by neutrons theory, that there has been a force acting between two bodies of distance d and mass m1 and m2, and that is what is the force acting on this. Here, it's a classical theory. Here it is kind of assumed that this interaction happens instantaneously. That means very high speed, and then it just happens immediately, and then only it happens. But if it happens, what is the gravitational, this Einstein's theory of relativity, general relativity, it says the information is carried by gravitational radiation. So it's like, in case of electromagnetic interaction, there is a photon exchange in between them. In case of strong interaction, there is a quark exchange or pion exchange in between them. Here there is a gravitational radiation which moves in the speed of light, and that's what is the details of the gravitational wave or general theory of relativity. Now, how do you detect them? How do you detect these objects? Now, how can these objects can be created, which will essentially, because if there are two very small mass objects and you say that they will create gravitational wave, we will detect it, it's essentially not possible. So what might happen is that there might be collapse of two black holes, and or two binary stars. They're just moving, and then they will keep giving you gravitational wave, and then they will come, and then at some point of time they might collapse. And when they collapse, just before that there will be a burst, and then that might be, now it collapses as you can see, and it will create another black hole, and then that might you can play it again. And as you can see, these are the binary stars, maybe two black holes or two white dwarfs or whatever, and then they are just rotating, and then they are giving you waves, and then at some point of time they just merge, and just before the merge they will give a burst, and that will be a gravitational wave which might come to our observatory. There might be something which might happen in the asymmetric neutron star, which is always moving, and then it's kind of giving you the wave all the time, and then you can see a behavior which will come as a background. And similarly, the compact binaries will give this kind of signal when this will happen. So these are the things that we try to understand, and we go to different observatories. Now let's talk about LIGO a little bit more. What is LIGO? LIGO, as you know, you all have kind of done interferometry experiment in your MSc days, I'm sure, and where the waves they generate, means when there is interferometric pattern which is generated, and from there you can study the different properties, and that depends on the length of two waves that interfere one over the other. Now what is done, a laser is kind of thrown, and then this gets reflected and then come back, another one goes straight and come back to mirrors, and then they interfere at this point of time, and then you start seeing the pattern, and they are of exact same length, so that the pattern is highly circular, and you see a nice pattern if it happens that nothing is happening. Now let's think of a scenario in this observatory where you have two arms, and then a gravitational wave hits here. And because of this gravitational wave, as it is a huge wave, so it might change the length of one of the arms. So let's say one of the arm has got elongated, another one will get a little bit shortened because of this small impact of the gravitational wave. Then the interferometry pattern will be different. So now when we are talking about the pattern, then we are talking about the distortion, because there will be a distortion in the pattern which can be measured of 10 to the power minus 21. This is what we are talking about, delta L by L, which is the strain that we are talking about here. So we have to have an observatory. There is no, it cannot be done by your normal interferometer. So there is an observatory which is in Livingstone, there are two arms, both of 4 kilometers, and then they interfere, and here is the interferometry pattern. This is one. Another one is, again, it's a Hanford observatory. So one is here in the United States, another one is here in the United States. There are two observatory, LIGO observatory, and there is another one which is in Virgo observatory, which is in Italy, Cassina, Italy, which is here. So now, what has been found on that particular day where gravitational wave was discovered, that if you look into the time, and as you can see, it's almost background, and suddenly during this point of time, about 0.2 second or so, there is a huge strain, huge jump in the signal. If one can see what is the frequency of it, and that has been seen both by Livingstone as well as Hanford, and this is the one which has essentially resulted in the discovery of the gravitational wave. And this is to be this is for the from the black hole merger. Now, interestingly, all these three, if you just look at all the three observatories which are there, and if you take data, because if there is a gravitational wave, all the observatories will see it. Means at least gravitational wave affect all the things on Earth. So if this guy sees this laboratory also should see, this laboratory also should see. And from there, if you try to make an estimate that where this binary collision happens, or where this black hole merger has happened, the star, this is what is the, and there are different observatories, of course, all over the world, who can also start looking, like some of them are looking at radio wave, some of them are looking at neutrinos, some of them are looking at gamma rays. So it may so happen that This is a very interesting topic. All of you must know about it, that gravitational wave is something which is supposed to be the collision of the black holes. Two black holes merge and gravitational wave is produced. But then gravitational wave can also be produced if two neutron stars merged. Now, if two neutron stars merge, there will be a very interesting thing will happen. In addition to the gravitational wave, because of this mass they are joining together, there will be photons which will come out, because the merger of neutron star creates all the heavy elements like beyond means gold, platinum, and all others are created there, and they will essentially be radioactive and they will essentially radiate. So what you will see is not only gravitational wave will be coupled with other kinds of wave, mostly gammas, and that tells that this collision is not because of the black holes but because of the neutron star. So this you should all try to understand that there is a difference between gravitational wave from black hole and gravitational wave from neutron star. Neutron star merger will give you gamma as well as the gravitational wave. Now, if I take all the things that exist today, this is what is the precision with which we can tell that where it is happening. This is what is the precision. And if you take all the observatories which are existing today, and this is what is the precision of locating where actually those black hole mergers happen. So what has been said now, that if there is an effort which is going on to build a LIGO observatory in India, in Maharashtra, and if we add that laboratory, and then the precision becomes like this. So that means by adding LIGO India in the whole graph, your precision of knowing where the black hole merger or neutron star merger is happening are much more precise. So that is why Government of India has been pushing very hard to get the LIGO project materialized. And this is where it is. It is supposed to be 2025. This is the artist picture. This is in Maharashtra, where there is almost no people around, and there are two arms which will essentially create your LIGO observatory. Now, I want to make one more statement here for nuclear physicists or high energy physicists, that neutrons and who are working in FAIR, for example, this neutron star merger, which is seen by gravitational wave, has a nuclear physics connection. Because as I said, that this will create new elements, and these elements are produced only by neutron star merger. You cannot just fuse proton and neutron and make in laboratory gold. Gold are not made in the laboratory. They are all made in heaven, basically, and heavy elements like platinum and others. So there have been calculations which have been done. So what we will do in FAIR, we will collide gold and we will create core of neutron star, and that will certainly give you an information which will be useful for understanding the neutron star merger even in gravitational wave. So there is a big connection between FAIR physics and the physics of gravitational wave, which is basically understanding the details of the neutron star and its merger. So now, does this gravitational wave observatory should stay? You see, this is what is the search for gravitational wave observatory, and you see where they have landed up. It's in Australia. It's for square kilometer array. It's near Perth, and you can see what is the inhabitant of that place. It is a 50,000 square kilometer array. It's size of Netherlands. There is no town. There are 29 sheep or cattle stations, and total number of people living are 110. Why that we have to go to a place where there is no people? Because the gravitational wave observatories or any observatories, these astronomical observatories, are catching the signal which should not be disturbed by the signal generated by, let's say, human or by anything which is worldly. So this is not there. So that is the challenge for people, astronomy people, to find out the exact location where they find. And this is what is the square kilometer array. There is similar thing in Ooty also in India, which is GMRT, which many of you might be interested to know. Now I almost go to the last section of my talk. As you have already seen that all these big experiments has their own challenges. We have to have high precision detectors, high speed detectors, and we have to have cameras which should run in megahertz and million pixels. And your camera may be the fastest mobile camera might take a few pictures in a second, but here I have to take 10 to the power 7 pictures in a second, and radiation hard electronics and radiation hard detectors. And these are all we are trying to build along with Bose Institute, and pandemic did not stop us. So some of you might identify yourself. This is, I believe, Shreya here, and there are other Indian colleagues who took part in testing our equipment, which is called gem detector, in FAIR in Germany during March 24 to May 4th, which is the main pandemic period, sitting at home. So this is a world science using World Wide Web to study or doing the experiment remotely. Now there is another one. If I do not mention this, this will be a little bit not correct. Is that all this could happen because, as you know, that the huge amount of data are generated. It's not only that experiments are large, the areas are large, it's heavy, but huge amount of data, and that data is to be processed, and that cannot be done by a single computer or a computer at a single place. The things all changed when this particular person who wrote a note statement concerning CERN W3 software releasing into public domain. And this has a story. You know, this is what is the beginning of World Wide Web. And this World Wide Web, which they call as W3, they made it a public domain. It's a public property. Somebody said that if it was not made a public property, but would have been a property of CERN, then the royalty that World Wide Web would have brought would have been enough to run CERN. They would not have needed any money from anywhere else. But then it was made to be a public, it was public property, and that is why everything is free. You don't have to pay anything to CERN because they discovered it. That, and you all know what is the impact of this thing. So now just to give you an idea that what is the kind of volume, data volume we are talking about. If you talk about large means LHC experiments and then put all the data in a CD, whatever CD compact disk if you have, and in that compact disk if you put one after the other, then the height will be like this. So this is where your aeroplane flies, and this is what is the size. So inside this stack, if somebody says you find quark gluon plasma or you find Higgs boson, it will take years. And then funding agency will not give you any fund after that. So what has been done is to club together all the computing centers, Europe, America, and India, and all other places. Whoever is free, they will give the job, and it's like a power grid. So this is what is running here, the grid computing even in VECC. There is another one. Of course, you have to have big data. So this is called Green IT Cube, where it is a hugely energy efficient. It is in FAIR in Germany, and I have been told that it's like 3 times less energy that it consumes. That's why it's called Green Cube. And astronomy, you see the amount of data that this particular experiment will have. Phase 1 science, 300 petabyte. And compared to the Facebook, which is 180 petabyte, Google 98 petabytes, and YouTube and others are kind of tiny in that comparison. So this is the data that you have to kind of process. This is itself the challenge. Now, when we spend a lot of money, try to understand things which are elusive, then what are the societal applications of that? And this essentially tells exactly the same equipment or similar equipment that can be used for radiation therapy, as has been pioneered at GSI, which is at FAIR site, for hadron therapy for cancer treatment. Now, I just want to go back to my small science again. Now, I started saying that small science is the basis, and then we went to big science, and I have discussed some of the big science projects where India is involved. Of course, it's not a complete list, but I want to make a statement which was made by Barry Barish, who got Nobel Prize because of the discovery of gravitational wave, and he is the main person who essentially spearheaded the gravitational wave or LIGO project. And this is what is his table. This is taken from his own slides. So what are the attributes between small science versus big science? What is the success is defined? If you are successful in a science project, in a small science, the success is defined by scientists, by creators, by inventors, or by peers. But in case of big science, the success is defined by managers, reviewers, sponsors, and peers. They tell, yes, you are successful or not successful, you have to have a lot of review. Now, who will take the decision? In small science, when you are doing your own experiment on a tabletop, the decision is taken by scientists. Okay, I will change the temperature, I will change the pressure, I will do this and that, creators and inventors. But in case of big science, again, it's managers, it's directors, and it's delegated, I mean, by somebody else maybe on their behalf. What is the flexibility of always flexible? You can just take everything apart and then put them together and do a new experiment. It's always creative. You can keep thinking and do something new. But in big science, when LHC is met, when experiment is met, you have to think 20 years ahead. And when you do once, it's very limited that almost nothing could be changed in between. Who will fabricate these experiments? In small science, it's an in-house craft work. That means you put the things together. You just maybe something you think that yes, this is how I will do it. But then this is an industrial approach in big science. So you don't do it in your lab. You buy the equipment from industry. And who are the team composition? Of course, in small science is predominantly scientists, because you do, I do, my student do, students do it, and then we have the experiment done and paper written. But in big science, it's all scientists, engineers, accountants, and all other project managers. Now, what is the visibility of the project? This, in case of small science, it's very private. Somebody is doing it in his own lab, somebody is doing it on his own table, and then getting the results out. But in case of big science, it's a public. Everybody knows what is happening in CERN. Everybody knows what is happening in FAIR. And the project process, in case of small science, it's opaque, because it's only in the mind of the people or the few people who are working on that. But in case of big science, it's transparent. At every level, it is reviewed. Everybody checks everything. As you know, that there is a collaboration review of 450 people says yes, then only paper is published. And so, we must make small science culture, which is basically understanding the basic of science, with big science culture, which is like an industrial approach. We have to have a concept and design in the small science, because you cannot change the theory. You cannot change Newton's theory or gravitational theory. You can make it a big, huge object with 17,000 ton weight, but then your concept is Maxwell's equation will not change. So you have to have the concept and design in small science. But when you do big science, you have to have a planning, then execution, solve technical problems. Again, in small science is crucial. So transition to science usage, again, small science will come. Finally, when you will ultimately discover Higgs, it's not a very big thing. It's just 2 photons coming out. And then you know that the mass of these invariant mass of these 2 photons are 125 GeV. And it is beyond background of 3 sigma or 4 sigma apart. And you say, yeah, hooray, I have done the discovery. And this is exactly like the discovery you do on your own, on your tabletop experiment. And this is how this laboratory collaboration and all put together, and the funding agencies. Now I just want to almost end with my own experience. When I started my career, which is my PhD, where, as you all know, that we are all studying the heavy ion collisions to understand the quark-gluon plasma. And my first experiment was using WA93 experiment, where I built a small detector which had about 8,000 scintillator pads read by CCD camera like your mobile phone, and this was transported to CERN, and that was my first time I went to CERN, did the experiment and wrote my thesis. This was 2,000 each camera, so 8,000 cells. The next step, again, it's not far from that, which is WA98 experiment. This is similar, but this has already increased to 26 cameras, and it has 55,000 cells. And then when we built an star, there are 80,000 cells, but this is not scintillator anymore. This already became a gaseous detector. Technology has changed. And then finally, we built another photon multiplicity detector for Alice, which had 200,000 cells. So starting from 8,000 to 55,000 to 80,000 to 200,000 cells. And now we have completely changed and gone to the different region of phase diagram, where we are building this complete neon chamber itself, where many of you are participating. Now let's go to our observatory because we have talked a lot about observatory, which is near you, which is in the Tiger Hills, Darjeeling. I don't know. I am sure many of you, most of you, have the experience of this winter morning at 4 o'clock. You get up and go to the Tiger Hill, put your cameras, put your lenses together, and start looking on the sky, eastern direction, and then you have all the cameras ready, and then you find something and you say, yes, I have it, I have found it, and that's the star that I have found, or that is what we call a sunrise. So thank you very much, and I am sorry for this delay in starting and all the problems that we have. Thanks a lot.
Thank you, sir. Thank you very much. It was really a very beautiful talk, and all the topics were very interesting. I hope everyone has enjoyed it. And big clap for you, sir. And so let us now start the question answer session. I request the audience, if you have any question, you can ask directly by introducing yourself first. Just tell your name, or you can write in the chat box so that it can be forwarded to sir. So we will take up questions now.
Sure.
Does anyone have does anyone have any question?
নাই নাই শেষের দিকে এসছে।
Maybe all of them are tired.
No, I
Maybe
don't
I have
think
a question.
so. There must be some.
Yeah, Rajendra, you can start.
Yes, yes.
Hello, sir. How are you?
Yes, hello. Yeah, we are doing fine in pandemic, whatever could be done.
Yes, nice to hear you after a long time,
Okay.
and it's
Yeah,
really nice talk. Uh,
thank you.
so we have a nice flavor about big science, and but sir, I just want to ask you. From India, we have a big science project like INO.
Mm-hmm.
Yeah, in your this presentation, you did not
Yeah,
touch
yeah,
much
yeah.
iron.
Mm.
But what do you think? I mean,
No,
how
I
that
know, I know. Yeah,
in
that's a very
future?
good point that you have raised, Rajendra. The intention was not to exclude for any reason. INO is there in my list, in the first list, but I did not include INO because mostly it's kind of the first thing is that it is inside India only, and that is how the project is done. I tried to cover multinational ones. Another one is most of the people they know about INO. So if anybody is having any specific questions on INO, I will be very happy to answer because all of us are somehow or other connected to INO project.
Because iron is, I mean, our big science project, and that's why I thought we will have some update and some news.
Yeah, so I can tell you, INO is the project. All of you, I think, just for those who do not know about it, INO to an extent is an neutrino observatory, and it will study the atmosphere in neutrinos, because as you know, neutrinos have oscillation. That means one type of neutrino gets converted to another type of neutrino. So electron neutrino go to muon neutrino go to tau neutrino, and these oscillations are basically studied by atmospheric neutrinos, which will pass through a 58 kiloton iron calorimeter, and it is a magnetized one, and then there will be bending of those, and from there you'll know the momentum, and from this path and the momentum you can know what is the oscillation. Now there are problems with INO from the almost for quite some time. This is a problem for other international projects also. This is basically the site to find, because as soon as INO needs a like at least 1 kilometer means earth overburden over this, because otherwise all the background to be stopped, and there are a lot of environmental groups they complained, and once the project has been moved from Tamil Nadu to Tamil Nadu Kerala border called Theni, and now also there is court case going on in Supreme Court of India, for getting the environmental clearance. And meanwhile, of course, time is passing by. So far as the detectors are concerned, the detector will be used with RPC, which are almost ready. But then it is now basically stopped there, and we are all waiting for Supreme Court verdict. When it happens, then we will know in which direction iron will go. But it's certainly an active project in India, and there are a very large number of people who are involved in this project. Okay.
Yes, sir. Thank you.
Sir, I have a question in this context.
Sure. Go ahead.
Sir, when we have something, we have to wait something for like a verdict or Supreme Court verdict. So it basically delays the science agenda. If we have a big science, then we already have to wait for 20 years. Or for LHC, like we have seen that the data taking started from, we are predicted it will start from, we started to predict the science from 2000 and then it's 2020. Now we are planning for FCC. So it's a long time project. So 20 years, 50 years.
You're absolutely right, Deeptak. And for a young guy like you, saying this is absolutely correct. But that is what is life. There are parallels to that. You might, I don't know if you know about superconducting super collider, which was the tunnel was built, and then because of the political reason, project, and there are, I think, quite a big amount of money was spent on that, then the project was abandoned. There is that is the biggest example of mega science project which was stopped midway. Now there is one of the astronomy project which is TMT, 30-meter telescope, that is now having similar problem, because they found, like I said, that for astronomy project you have to find the sites where there is no people, because otherwise it will interfere with the background. So TMT has a problem. They found a place in Hawaii, and then Hawaii, the local people started objecting. Similar problem as INO is facing basically. Here also local people, but there I hope that that's not a political problem. Here it's a political parties are essentially complaining, and that has essentially stopped any progress in 30-meter telescope. All the instrumentation work is being done, but nothing is happening outside. Now, so far as INO is concerned, you are right, because the problem is not that it's taking 20 years. Let it take 20 years, but we know after 20 years we will have a physics, right? Like LHC, everybody knew that it will come up and this year maybe it was delayed by 2-3 years, but it's not a big one. But the problem with INO is that as it is depending on verdict of the Supreme Court and the environmental matter, we do not know which direction it will go. That is what is in my opinion, is the bigger problem. Of course, authorities have been trying to find some other places, like some of you might know that in Jadugoda mine, near Jamshedpur, a lab has been set up where there are some experiments are being set up just to see that if there's something could be done for the people who are interested in underground laboratory research. But this is certainly not a replacement of INO, because that is a much bigger issue. So I agree with you, this is a problem, and at this point of time we only have to wait for Supreme Court. Okay. Hello, do you hear me?
Yes, sir. Hello.
Okay.
So just what I am saying, that if I avoid this problem, we just avoid this political problem. There is no political problem. Everything is smooth and fine.
Right.
Then still we have to wait for a 10 to 15 years for data.
That wait is enjoyable, right? And we are all waiting. Yeah. Yes. Go ahead.
And for a guy like me who is just in the final year of PhD or completing his work, there is no guarantee that I will be there or not when the result will come out, and it may be that some of us will be out of science.
Yeah, I understand your point. So let me tell you one example, two examples. One is of course INO, which we have discussed at length. Another one is, for example, FAIR. FAIR is the project. Many of your friends are involved in FAIR. Now, of course, whoever are doing PhD now, because FAIR is supposed to give beam in 2025, and then maybe first results after that. So you have to wait. Now, what in my opinion, there is the positive side of whole thing. of course, which is not true for INO, because if you have to wait only for Supreme Court, then nothing could be done. But if you have to wait that yes, I have to be ready 20 years to build the things. You ask your seniors, including Shoykot, Siddharth and others, they spend most of their time in building detectors and equipment for doing LHC experiment, which took place after they completed their PhD or just at the time of completion of PhD. So that time you learn a lot, and when you learn a lot, of course there are these some projects or others, some physics interest all over the world that will attract you, and you will be able to do something about this. But if it happens to be the case that yes, there is nothing to be done, which is intellectually challenging, whether it is detector building, whether it is electronics, whether it is computing, of course that is very frustrating. So if that happens to be the case, I am sure one should start thinking about something fundamental and then maybe change something and then do something else. Otherwise, if it happens that no, I have to only wait for 5 years for beam to come, by that time I have to make my detectors ready, that itself is a lot of work, and that should keep going. Means that's, you should not feel disheartened that no, I have to wait for data to come and then only I'll do physics.
Thank you, sir. So we just have to wait for CBM to get it.
Sure.
Thank you, sir.
But sir, the point came up here, like time period. Now let's say for other experiment like in LSC or in FAIR. I mean, things are going parallel. Like we are building detector, we have our physics motivation, and site are chosen by the time so that everything synchronized at some time, and we will be we will be able to run our experiment. But as we told now that for INO, now our detector is ready, and we are waiting from something political clearance and something here from Supreme Court. So this is in that way is not a good sign.
This is certainly not a good sign. I cannot defend something which is
at the same time, like we had some rich physics, neutrino physics goal, of course. That is why we are thinking for INO. But by that time, we will have some other experiment like Dune. They are also a competitive experiment. So after some time, we will lose our money, our physics idea, motivation, our hardworking researcher, everything. So yeah, in that way, nothing is going, I think, in right direction.
Actually, there is in history also, history of science, there are examples that people have done a lot of work, preparatory work, and then it has been abandoned. ILC we have been talking about for quite long. We do not know whether ILC will come, because people have started talking about FCC. At some point, it has to have something else. So my point is very simple, that yes, when we are student doing PhD, if we have science output immediately, which we write papers, that is the best one. But then one should not ignore the scientific, intellectual things that we are doing while preparing this. So that has to be considered. Now, so far as ION is concerned, I only hope, sincerely hope, that this phase will go. I know how the INO project management has been handling the project. They have already made a mini prototype, which is, I think, VECC had a 30 ton. They have made 1 kiloton, I think, in Madurai, and which is being read by all electronics and others. And they are doing very extensive cosmic ray research with this. And exploring that if some new physics could be done. So the students who are there in INO school are, of course, getting trained nicely, but then there is of course, question mark, which I cannot kind of defend more than that.
Mm-hmm.
Okay. So I think Tapan sir had a question.
Sure. Hello, Tapan. How are you?
Wrote in the chat box.
Yeah, nice to see you.
Nice to see you, Subhasis. Yeah, I joined your talk a little late.
I started late also, so go ahead.
And that I realized also. And when I joined, you were talking about SK, Square Kilometer Array, the Australian project.
Yeah.
So this is a big project, and let me, instead of asking a scientific question, let me ask a question which was asked by Rajendra and one before.
Deepta.
So there are many mega science projects in India now. If I look at this SK consortium, India consortium, and I see that 75% of them are theories at this point. And you say that it will be ready in 5 years. Let's say five. Yeah, in international, it is mostly, if it is approved, instead of five, it may be 5, 7. So how our students, I assume most of the students are from both institute who are there listening to this, and how our students are getting trained in hardware, in fair, sun and star like that, how they can participate in this type of mega science projects in India, what is happening in terms
Yeah,
of getting
yeah,
missions and all that. Because
yeah.
you are now attending all those. So I think we should spread our knowledge so that people are aware of our hardware capabilities. I'd like to get your
Sure,
opinion.
sure. Now that's a very good question, Tapan. Let me give a status report. Of course, one means biggest one is LIGO. Of course, SK is important so far as funding part is concerned, which is LIGO India. Because LIGO means LIGO part of my talk was just before SK, so you might have missed it. So whole international community of LIGO is waiting for LIGO India, because that will essentially pinpoint or make the precision of knowing where the black hole merger or neutron star merger happens with something like several orders of magnitude better. So they are all looking for LIGO India project, and government of India is kind of gung ho in getting this project done. Now, LIGO India is basically it's a construction project, but then you have to have these lasers and then interferometers and all other things, which are high precision equipment. So, if we talk about 2025, it has to be done. I am also doubtful that there is a much scope of doing R&D on that. So, most likely the construction, all these things are being basically spearheaded by RRCAT, Indore, and because they have been given the job, it has become a DAE project. So they will be able to do very very nicely, no doubt about it. So I think in LIGO there is not much. There will be some scope, of course, because otherwise it's a Ayuka, I think, who is taking part of Pune as the physics part of it. So there is not too much of opportunity of this, but some opportunity. But so far as SK is concerned, as you mentioned, I think SK is in a much better position. Why? Because SK, the team who is working on SK, which is basically led by TIFR and Hyderabad campus, and they are the one who are basically legacy of UT, this GMRT team. So as you know, that GMRT is the means people say about the most successful Indian mega science project, because GMRT a good fraction of the time is being used by outsiders, not insider by Govind Sarup. So that team has a very good experience, of course, in both in making the telescopes ready as well as analyzing the data. LIGO team, of course, has a good experience in analyzing that data because they are in this collaboration. So I am not that much worried about means my impression about SK is much better, and there is a big part they are doing basically on software part, that means data challenge part, which is basically they have given to Tata Consultancy. And Tata Consultancy, even you may see in their CNN advertisement, they are advertising that they are participating in SK. That is very interesting that one company is advertising that they are participating in SK. Now comes about your FAIR and CERN. FAIR, as you know, that FAIR has both nuclear physics as well as high energy physics. And FAIR, so far as muon chamber is concerned, we are doing everything ourselves. So that R&D, whoever are students there from both Bose Institute and other places, they are, I think, getting well trained because of the main reason of FAIR Phase 0 program, because we started getting data, gold plus, means lead plus gold collisions, which is at 1.2 GeV, and they are analyzing the data and getting lambda particles and others. So they are getting trained well. I think both at CERN, because CERN, of course, has a legacy of it. So that is what is my input at this point of time. And I can also add that there are several meetings on mega science project which was spearheaded by Professor Vijay Raghavan, Principal Scientific Advisor. Separate projects separately, and I had the opportunity to attend two. One is for CERN, another one is for FAIR. And he is very much positive about all these things, and his goal is, of course, to see that things are done in India, which is, of course, the goal of the government. So that is all I can give you input at this point of time.
Yeah, no, that's very good. My question is only for the younger generation. How can we advertise that within our community, high energy phase community, where I think in both combining CMS and ALIS, we have a large number of manpower generated compared to any other mega science project. How can we advertise that this manpower is available even for simulations? It goes to Tata, which is good. But if they can hire our people, generate manpower, that will generate
Yeah,
our manpower can be used for that.
yeah,
Our
that
person
is
power can
that
be used
that
for
is
that.
that is a, that is a
Can
very good
we
point.
advertise in proper channel so that
Mhm.
we are noticed in a proper way, and we can get our students can get opportunities.
Yeah, that I think is a very good point. I think at this point of time there is no forum like that somebody has a central program or pool which says that. But I agree with you that if something could be done, because I think there is some mega science vision scheme which is coming up from PS's office, and that could be certainly a big input, because it has been said by many fora that you see we have many students, and you think about what will happen to those students. We are talking about that the students, you generate students, you train people, but then what will happen to them? So this is said, this has been acknowledged also, but then the solution has to become in a bigger scope, not just you or me can solve it in personal level, right? So we are pushing for it, and it is. I would request all of you from wherever you are just to keep pushing wherever you find some fora on that. Okay.
Thank you.
Thank you. Any other comments, questions?
If no, then we will close this seminar for today.
Mhm. Okay.
Okay. So thank you, sir. Thank you, everyone, for joining. And
I also would like to thank all of you.
yes,
Again, I'm
yes,
sorry for the
yes.
initial disturbance, but I'm sure we will all
No,
enjoy
sir, it's
doing
all
this
right.
together.
But the talk
For,
was really nice.
so thanks a lot, and I'm sure your
Yes, sir.
next of the talks will also be
Rajitda is
equally
speaking.
interesting.
No,
Yeah.
no,
Yeah.
no, no.
Rochiji, do
I
you
was
have?
just thank you. No, no.
Okay, okay,
Yes,
okay.
yes. Thank you,
Thank
sir.
you, thank you, thank you. Okay,
Thank you,
then
sir.
take care
Bye.
and enjoy. Bye. Bye.
Bye.
Bye.
Okay, sir. Yes, sir. Okay.